In this video tutorial, we will discuss reactions involving aromatics, alcohols, aldehydes, and ketones. In our previous lesson, we learned that aromatic compounds are those that contain a benzene ring. So be careful, just because your organic compound has a ring structure doesn't mean it's an aromatic. Although these two examples look like benzene, without the delocalized electrons, they will undergo chemical reactions similar to those found in straight-chain alkanes, alkenes, and alkynes as discussed earlier. As an example, cyclohexane will react exactly as a regular alkane would, and a reaction with bromine still requires heat and UV light to produce a alkylhalide, whereby a substitution reaction occurs with heat and or UV light breaking up the bond between the two bromine atoms, which makes them very reactive, allowing a substitution reaction to occur whereby one of the bromines switches places with one of the hydrogens from the cyclohexane, resulting in the bromination of this ring structure and the formation of HBr. So again, this is the exact same chemical reaction as if it were a regular straight chain alkane. Looking back at our previous example, we saw that heat or UV light is used to break up the diatomic bromine, which in turn allows the H and the Br to switch places, thereby brominating the alkane and forming the HBr. So having this ring structure doesn't really change the reaction, whether it's a straight chain or a ring. The same goes for ring structures that contain double bonds and or triple bonds. As we saw previously, halogenating an alkene or an alkyne does not require heat or UV light. Room temperature provides enough energy to activate this reaction, since the double bond and triple bonds are quite reactive already. So here we would have the double bond break, turning into a single bond, thereby opening up two new bond sites, where each of these bromines can then be added on. Similarly, the halogenation of a ringed alkene or ringed alkyne only requires room temperature, and once the double bond breaks, forming a single bond, two new bond sites open up, and our bromine atoms can be added on. So, as you can see, being in a ring structure doesn't make it more special or different from the chemical reactions that occur with a straight chain alkane, or a straight chain alkene, or a straight chain alkyne. So, what happens if you do try to halogenate a benzene ring? As you'll recall, benzene is quite stable due to that delocalized electron, and this stable ring doesn't normally accept extra atoms, as such addition reactions cannot occur when you halogenate benzene. So instead of an addition reaction, it will undergo a substitution reaction. In this example, one of the hydrogens on the benzene will switch places with the bromine, resulting in the formation of HBr and also the bromination at one of the sites for the benzene. You'll notice that iron 3 bromide is written over top of the arrow, so that indicates that the iron 3 bromide is being used as a catalyst. It's not a reactant, it's not a product, but it is there to help speed up the reaction rate. Now, as I mentioned earlier, this is a substitution reaction. A common mistake students will make is they'll think that this is an addition reaction. When benzene is drawn like this, it's very easy to think that these are double bonds. And as we saw earlier, when you have a double bond that is being halogenated, so halogenated means you are adding halogens to it, the double bond breaks, becoming a single bond that opens up two new attachment sites, allowing each bromine atom to be added on. So this will be an addition reaction. But as we learned earlier, benzene does not have any double bonds, it does not have any single bonds. Instead, it is a resonance structure with 4/3 bonds. So while these double bonds are easily broken, allowing for addition reactions to occur, these delocalized electrons in the 4/3 bonds are quite stable, only allowing substitution reactions to occur. So as I mentioned earlier, drawing the benzene ring like this makes it easy to think that it's a double bond that breaks, forming this addition reaction product. But you have to remember that these are not double bonds. They are very stable 4/3 bonds. As such, it might be helpful to draw the benzene ring like this with a circle inside instead of the three what looks to be double bonds, in order to remind you that there are no double bonds present, so only substitution reactions can occur. Now, if you halogenate the benzene ring further, you can add on the second halogen at 3 different locations. on the number 2, on the number 3, and on the number 4 carbon, resulting in 1,2-dibromobenzene, 1,3-dibromobenzene, and 1,4-dibromobenzene. Unfortunately, a lot of chemists prefer to use the common naming system instead of the IUPAC naming system. So if you ever see the term ortho-dibromobenzene or O-dibromobenzene, that means the halogens are side by side or adjacent to each other. When you see meta-dibromobenzene or M-dibromobenzene, it means that they are separated by one carbon. And if you ever see para-dibromobenzene or P-dibromobenzene, it means that the halogens are on opposite sides of the benzene ring. However, for this course, we will focus only on the IUPAC naming system. We will not be using the common naming system. I just want to make sure that you are familiar with it before you head off to post-secondary, where your professors will almost certainly be using the common naming system. Now, there are 2 other substitution reactions involving benzene that you may encounter in this course. The first involves the substitution of nitric acid, where a nitrogen and 2 of the oxygens from the nitrate ion switch places with a hydrogen on the benzene ring, resulting in the NO2 being latched onto benzene, and then one of the H's and O's, and this H creating water. Since water is released in this substitution reaction, it is also considered to be a condensation reaction. You'll also notice that H2SO4 is written above the arrow, so this substitution reaction is acid catalyzed. Looking down here, we see a very important reaction that we will be using quite a bit in our course, and that is the substitution of an alkyl halide, so an alkane with a halogen attached to it. I like to think of this alkyl halide as a delivery device. So the halogen acts as the front of the truck, while the hydrocarbon, the alkane at the back, acts as the cargo. During this substitution reaction, the hydrocarbon and the alkane switch places, and the alkane has now latched onto the benzene ring. Meanwhile, the hydrogen has latched onto our little transport truck, the halogen. The reason why I like this analogy so much is that whatever you have in the cargo hold gets latched onto the benzene ring. So in this example, we had ethane, 2 carbons, in the cargo hold, and that's what got latched onto the benzene ring. If I decide to put a propane in the cargo hold, 1, 2, 3 carbons, then a propane would be substituted into the benzene ring. If I change this to a butane, 1, 2, 3, 4 carbons, this too becomes a 4-carbon, 1, 2, 3, 4 butyl branch substituted into the benzene ring. So whatever fancy, weird hydrocarbon you put in the cargo hold, well, that's what's going to appear and be substituted onto the benzene ring as well. So this reaction will be very helpful for us during our synthesis problems, where we can use this delivery device to add on, or substitute in rather, different aspects of the molecule that I want you to create or synthesize. As a reminder, aluminum chloride is written above the arrow, so it is being used as a catalyst to speed up this reaction. So looking back at our flow chart, let's summarize the 3 major reactions we just discussed involving benzene. As you can see, all 3 of these reactions are substitution reactions. In the first one we looked at, we substituted a halogen, and in return we created a hydrogen halide, and then whatever halogen you had got latched onto the benzene ring. In this case, iron 3 bromide is used as a catalyst. Then we talked about the substitution of nitric acid, where NO2 is latched on, but water is also a product or a byproduct of this reaction, and H2SO4 is used as a catalyst. Then finally, the last one, aluminum chloride is used as a catalyst, and we substituted an RX, where R represents some sort of alkyl branch, so whatever we have in our cargo hold. And there's my halogen acting as the truck, the delivery device. So whatever you had in the cargo hold gets latched on, or rather substituted onto the benzene ring. And in return, a hydrogen halide byproduct is created as well. Alright, now the next set of reactions we'll be looking at involve the alcohol functional group. When an alkene reacts with water, an addition reaction occurs. First, the double bond breaks, opening up 2 new sites, allowing the hydrogen and the hydroxide from the water to latch on. This, of course, follows Markovnikov's rule, where the rich get richer. So whichever carbon has more hydrogens gets the hydrogen. So in this case, the terminal carbon over here has 2 hydrogens attached to it. It gets the hydrogen, while the one in the center only had 1 hydrogen. It should get the hydroxide instead. So 2-propanol is your major product. while 1-propanol is your minor product, where the hydroxyl group is now attached to the first carbon atom, and the hydrogen gets attached to the second carbon atom. Again, sulfuric acid is written above the arrow, so it is a catalyst in this chemical reaction. If we look at the chemical reactions flowchart, this reaction converts alkenes into alcohols. It is an addition reaction, also known as hydration, because a water molecule is added in. Sulfuric acid is used as a catalyst, and it also follows Markovnikov when determining where the placement of the hydrogen and the hydroxide will be. So when the multiple bond breaks, which side is more likely to receive the hydrogen and which side is more likely to receive the hydroxide? Because both possibilities are going to occur. So we've now seen how alcohols can be created from alkenes, but they can also be produced from alkylhalides. This would be a substitution reaction where the OH and the Br switch places to produce an alcohol and a metal halide. So you must react your alkylhalide with a strong base. Typically sodium hydroxide is used. And if you want a different halogen here, let's say you wanted to substitute in a chlorine atom instead, then sodium chloride would be produced as a byproduct. Or if you wanted fluorine, then sodium fluoride would be your byproduct, and so on and so forth. Looking at our flowchart, we are converting an alkylhalide into an alcohol. It is a substitution reaction with a strong base, often sodium hydroxide. Not only do you make an alcohol, but a salt is a byproduct of this reaction. So as a reminder, in chemistry, the word salt is generically used to mean an ionic compound that is soluble in water. In this case, sodium fluoride, if we're replacing with a fluorine over here. Or if we wanted the bromine, as we saw originally, the salt would be the sodium bromide. Salt. Now, if you notice in my summary, I wrote the number 1 here with the degree symbol, and that means primary. This means that this reaction only occurs with primary alkylhalides to produce primary alcohols. As a reminder, primary alcohols are those that have the hydroxyl group attached to the terminal carbon, and this carbon is only attached to one other carbon. So the molecule spreads out in one direction only. Same thing with the alkylhalide. The carbon that is attached to the halogen is only attached to one other carbon, so this carbon can only spread out in one direction as well. So primaries are usually found at the end on a terminal carbon, which is attached to one other carbon, allowing it only to expand in one direction, while secondaries are attached in the middle somewhere and can be attached to other carbons, moving off in 2 separate directions, while tertiaries are attached to 3 other carbons, allowing them to move in 3 separate directions. Now, the reason why I mention this is because primary alkylhalides turn into primary alcohols. If you try to add a strong base to an alkylhalide and it happens to be a secondary or tertiary alkylhalide, as we saw earlier, this would result in an elimination reaction, not a substitution, forming an alkene, water, and your metal halide, so the salt. So you notice this is a secondary alkylhalide because the halogen is sprouting out from this carbon, which is attached to 2 other carbons, allowing it to move off in 2 separate directions. And during this process, the H and Br get removed or eliminated, with the bromine latching onto the sodium, creating your sodium bromide metal halide in this case, and the hydrogen latching onto the hydroxide, forming water. Once eliminated, these bonds can collapse to form the double bond over here. So this reaction was summarized earlier in our flowchart, showing how alkylhalides can be converted into alkenes. Notice the similarities between this reaction, alkylhalides turning into alkenes, and this reaction, alkylhalides turning into alcohols. They both involve the reaction of a strong base, but because this is a primary alkylhalide, it results in a primary substitution reaction instead, as opposed to secondary and tertiary alkylhalides. When they react with a strong base, an elimination reaction occurs, forming the alkene. So please be careful. Only alkylhalides, where the halogen is attached to a terminal carbon, can react with strong bases to form a primary alcohol. Again, the primary alcohol has the hydroxyl group attached to a terminal carbon as well. Meanwhile, a secondary or tertiary alkyl halide will react with a strong base, where the halogen is not attached to a terminal carbon but somewhere in the middle, will react with a strong base in an elimination reaction to form an alkene. So elimination reaction to form an alkene with H2O and the salt, the metal halide, as a byproduct. Alright, so very similar chemical reactions with totally different end results, and it's all dependent on the location of the halogen. Is it on the terminal carbon, as you would see with a primary alkyl halide, or is it somewhere in the middle, as you would see with a secondary or tertiary alkyl halide? Now, most organic reactions are reversible, so once you have created your alcohol, you can reverse it back to its original reactants. So let's take a look at these two reactions. If you substitute your alcohol with a hydrogen halide, the hydroxyl group and the halogen, in this case chlorine, will switch places, forming your alkyl halide and water molecule byproduct. So on our flowchart, I've summarized it by saying it's a substitution reaction using hydrogen halide, like HCl, HBr, or HF, depending on what halogen you want attached to your hydrocarbon, so in this case Cl, but we could easily replace it with a fluorine, or a bromine, or an iodine, whatever. And in addition to the alkyl halide that is produced, a water molecule byproduct is also created. Now, when you heat an alcohol in the presence of sulfuric acid, so that's what this symbol means, heat. And just like the catalyst, it's usually written above or below the arrow, either or, it doesn't really matter. Well, heating the alcohol in the presence of sulfuric acid will result in an elimination reaction, producing an alkene and a water byproduct. So here the hydrogen and the hydroxide are eliminated to produce a water molecule byproduct, allowing the bonds to collapse, resulting in the formation of a multiple bond. So in this case, a double bond, creating an alkene. So if we summarize this reaction, we see that we are eliminating, or in this case dehydrating, a alcohol into an alkene. We call this reaction dehydration because you're removing or eliminating the water molecule. This of course requires sulfuric acid as a catalyst and also heat. Now, alcohols can also react with one another in a condensation reaction. So condensation reactions are a type of substitution reaction to form an ether. Now, I don't like how the textbook wrote out the chemical equation. I personally prefer to show the hydrogen and the hydroxide side by side to help the reader visualize how they will be combined together into an ether. So there we go. I've rewritten this equation. So I put the hydrogen and the hydroxide side by side. And now it's easier to visualize how this hydrogen and this CH3 are going to switch places or substitute in. So when I remove this H and the OH out of the way, I can bring these two together over here to make my ether and the water molecule byproduct. Again, sulfuric acid is written above the arrow, so it is acting as a catalyst. Since water is produced, it is a condensation reaction, which is a subcategory of a substitution reaction. Looking at our flowchart, this is summarized by the condensation of two alcohols using sulfuric acid as a catalyst to produce an ether. Now, if you've been paying attention, there is a problem. Let's say I've got a beaker full of ethanol. So this is ethanol, 2 carbons, 1 hydroxyl. 2 carbons, 1 hydroxyl. If I add sulfuric acid catalyst and heat, a hydrogen from one of the alcohols and a hydroxyl from the other alcohol will combine to make water. And once they are gone, we can attach these two together to create an ether. But if I add heat and sulfuric acid catalyst to these alcohols, an elimination reaction can occur where the H and OH pop out, producing a water byproduct, allowing these empty bonds to collapse into a double bond. The same thing would happen to the second molecule here. H and OH pop out, bonds collapse, producing a double bond and your alkene. So that's weird. I'm adding sulfuric acid and heat and getting one type of reaction. But if I do the same thing down here, heat and sulfuric acid, water also pops out. But now I form an ether instead. Sadly, your textbook does not explain why this occurs or what the difference is between these two reactions. They literally show you this reaction on one page, and then the very next page they show you this reaction, and they don't make the connection between the two. Super annoying. But after some digging in my university textbooks, I've come to realize that if you heat these two alcohols at 180 degrees Celsius, you will create an alkene. But if you heat it at 140 degrees Celsius, you will create an ether. So just be aware that the environmental conditions are especially important for organic reactions. Just changing the temperature a little bit will result in totally different products. So when it comes to organic chemistry, not only do you have to worry about how to create your product, you have to worry about how to avoid creating byproducts or competing reactions that you do not want. And in the end, you'll probably spend a lot of time purifying your final sample to get rid of those extra byproducts that are unwanted. Alright, so alcohols. If you add sulfuric acid, but you heat it at 180 degrees Celsius, it will undergo a dehydration or elimination reaction. So water pops out, but it's due to elimination, producing a multiple bond, creating alkenes or alkynes. On the other hand, heating this alcohol at 140 degrees Celsius in the presence of sulfuric acid will also have water pop out, but this is due to condensation, or it's a substitution reaction involving two separate alcohol molecules, producing an ether instead. Alrighty, and that is summarized over here. Alright, now I know that when most students look at this flowchart, they are very stressed out. It looks very, very complicated, but the good news is we are done the top half, and the top half is the hardest part. Although the bottom half looks just as complicated as the top, it's really just two types of chemical reactions repeated over and over and over again. So nowhere near as complicated as what you see at the top. Alright, let's begin. Oxidation of an alcohol. Alright, so as you recall, when you're oxidizing a chemical compound, you are either forming more bonds with oxygen or less bonds with hydrogen, or both at the same time. So in this case over here, I've got one bond with oxygen. This one's I've got two bonds with oxygen, and this one I've got three bonds with oxygen. So each time we're going further with the oxidation process, you're forming more bonds with O. Now, for this unit, we're going to focus only on the organic molecule. Is it being oxidized? Is it being reduced? Remember that when it comes to oxidation, if you're having one compound being oxidized, the other compound is being reduced. So they occur at the same time, which is why we call them redox reactions. You can't have one without the other. But like I said, with organic compounds, organic reactions, for this course, we're going to focus only on the organic molecule. Is it being oxidized or reduced? We're not going to worry about the oxidizing or the reducing agent, so the compound that causes the oxidation or the compound that causes the reduction. So when you oxidize a primary alcohol, so as a reminder, a primary alcohol is one where the hydroxyl group is attached to a terminal carbon, so it's got to be at the very, very end and only goes off in one direction. If you oxidize a primary alcohol, you will result in an aldehyde. And as a reminder, the aldehyde always occurs on a terminal carbon as well. So the very end of the chain, and it only goes in one direction. Now aldehydes can be oxidized one more time, producing a carboxylic acid. And again, a carboxylic acid also occurs on a terminal carbon, allowing the carbon chain to extend only in one direction as well. Alright, so the oxidation of a primary alcohol, one on the terminal carbon, results in the formation of an aldehyde, also a terminal carbon. Further oxidation results in the formation of a carboxylic acid, also on a terminal carbon. So there we go, primary alcohol, oxidize it once, turns into aldehyde. Oxidize it twice, turns into carboxylic acid. Typically, the oxidation process is controlled using potassium permanganate or dichromate in the presence of sulfuric acid. Again, we're only focused on the organic compound, so just write square bracket O to symbolize the oxidation process is occurring. Now, if we're dealing with a secondary alcohol, meaning the carbon atom from which the hydroxyl group is sprouting out from is attached to two other carbon atoms, so it can go in two separate directions. We've got a secondary alcohol. If you oxidize that one, it turns into a ketone. And if you recall, the difference between a ketone and an aldehyde is the aldehyde is always at the end of the carbon chain, so it's always on a terminal carbon, while the ketone is in the center somewhere with two other carbons on either side of it, allowing it to spread off in two different directions. So the oxidation of a secondary alcohol results in the formation of a ketone, where once we only had one bond with oxygen, we now have two bonds with the oxygen atom. If you try to oxidize the ketone again, there will be no reaction. With a primary alcohol, you could oxidize twice, because the CH bond is easy enough to break, allowing us to substitute in a hydroxyl group. So now you've got 3 bonds with oxygen. However, with a ketone, you're surrounded by carbons, and the CC bond is too strong to be broken apart, at least in this course. As such, we can't form another bond with oxygen, and this one is already maxed out, so further oxidation is not possible. Looking at our flowchart, we see that alcohol can be oxidized once, turning into a ketone, but that's it. It's a dead end past that point. Finally, with a tertiary alcohol, as a reminder, the carbon from which the hydroxyl group is sprouting out from is connected to 3 other carbon atoms, allowing it to move off in 3 different directions. But as I said previously, because the CC bond is too strong and cannot be broken, at least in this course, and this oxygen has already reached its maximum number of bonds, 1 bond with the C, 1 bond with the H, oxygen can only form 2 bonds, there's no more room to form more bonds with the oxygen. You can't add another OH to any of these groups over here because the CC bond is too strong. You can't put a double bond to this oxygen because it's already filled to the capacity. So further oxidation, not possible. And if you look at our flowchart, there is no oxidation of a tertiary alcohol. Only primary and secondary alcohols can be oxidized. Since reduction is the exact opposite of oxidation, we can revert our final products back to their original reactants using reduction reactions. This typically involves the controlled reduction with lithium aluminum tetrahydride catalyst, with the addition of heat and pressure. As a reminder, with reduction you're forming less bonds with O or more bonds with H. And because you're forming more bonds with H, we can also call this a hydrogenation reaction. Just be careful that you don't call it a hydration reaction. Hydration means you're adding water. Hydrogenation has the word hydrogen in it. You're adding in hydrogen instead. All right? They both begin with a hydra, so they're very confusing and they can be mixed-matched sometimes. So hydrogenation, adding in hydrogens, or a reduction process. Hydration would be adding water, which is not applicable in this case. All right, so going in this direction, we have oxidation occurring. And going in the reverse direction, it is reduction. So forming more bonds with O or less bonds with H is oxidation, while forming less bonds with O or more bonds with H is the reduction. Now you'll notice I was able to reduce an aldehyde to an alcohol. I was able to reduce a ketone to an alcohol, but this step over here does not allow me to reduce a carboxylic acid back to an aldehyde. So there is no reduction process directly from this step to this step. This is because the reduction of carboxylic acid is too quick. It doesn't really stop at the aldehyde step. It just bypasses and goes straight back to an alcohol. So be aware, aldehyde to alcohol you can reduce, ketone to alcohol you can reduce, but if you try to reduce a carboxylic acid, it will directly go back straight to the alcohol. It will not stop at this step. The reaction is too quick. So if you want to turn a carboxylic acid back into aldehyde, you got to reduce it back to an alcohol first, then oxidize it one more time and stop at this step. Alrighty. Alright, let's try some sample questions. These ones over here are pretty straightforward, so let's move on to the next one. Here we go. Let's give these ones a whirl. Let's try the first one together. I see that we have a primary alcohol over here. So primary meaning that the hydroxyl group is attached to a terminal carbon at the very one end. And we've got sulfuric acid and heat being used as a catalyst and also an environmental condition. Looking back at my flowchart, we can see and focus on alcohols. With alcohols, if you use sulfuric acid and heat, depending on the temperature, you might get 2 different products. So let's write them both out. Let's start off with this one. At 140 degrees Celsius, we will create a condensation reaction between 2 alcohols to create an ether. And over here we have a 1, 2, 3, 4, so butanol. I'm going to convert this condensed diagram into a line diagram. So 1, 2, 3, 4 for the 4 carbons inside. Just be careful. A common mistake students will make is they'll say, oh, butanol, 1, 2, 3, 4, 1, 2, 3, 4, and then they'll just put an H over here. But by doing so, you've only made 1, 2, 3 carbon atoms. That's propanol instead of butanol. So be careful. Count out the 4. 1, 2, 3, 4, but then don't forget to add 1 more for the hydroxyl group. Okay. Now, since this is a condensation of 2 alcohols, I will need a second one, which I'll color in red. And my personal preference is to put the 2 hydroxyl groups side by side, so it's easy to visualize how these 2 molecules will connect. From the summary on our flowchart, we see that water is produced, during this substitution reaction. So I'm going to take one of the H's, one of the OH's, doesn't matter which one you choose, and I'm going to bring them down over here, giving me the water molecule byproduct. Once those two are gone, I can see how these two parts can be connected together, creating the ether 1-butoxybutane, as well as the water molecule byproduct. This, of course, occurs at 140 degrees Celsius. At 180 degrees Celsius, however, an elimination reaction occurs where one of the hydrogens and hydroxides is removed. So I'll take a hydroxide from one side here, and one of the H's that's not shown here, they together will be eliminated to produce water, opening up two new bond sites that can collapse, forming a multiple bond, in this case the alkene, but1-ene, as well as your water molecule byproduct. And there you have it. Now, on a test, I would have to give you more details. I'd have to tell you this one over here would be either 140 degrees Celsius or 180 degrees Celsius. But if I don't tell you what the temperature is, you must give me both potential products. But on the test, I definitely will give you the actual temperature itself. All right, let's try two more, and I'll leave the rest up to you. So let's try C and D. But let's start with C. So here we have a secondary alcohol, and it's reacting with a hydrogen halide. Looking at our flow chart, I see that an alcohol reacting with a hydrogen halide is a substitution reaction, and water will pop out. So it can also be called a condensation reaction. In return, an alkyl halide will be produced. So looking back over here, the halogen and the hydroxyl group will switch places. So anytime you see an H and OH, just think of water. Now again, I'm going to translate all of this into a line diagram because your unit test will almost exclusively be using line diagrams. Very rarely will you see it in a condensed or complete format. Alright, so once the OH and the Br have switched places, we will produce the water molecule byproduct, and the bromine will now be substituted into the organic compound. I'm going to put a plus sign to show that these are two separate molecules that are created as a product of this reaction, and we're done. So hopefully you see the benefit of writing out these chemical reactions on a big giant flow chart to help you visualize how everything is put together, rather than looking at individual slides, all 48 of them. Alright, let's take a look at D now. I've got an alkyl halide reacting with a strong base. So there's my alkyl halide, but as we saw previously, reacting it with a strong base can result in two different chemical reactions. If it is a primary, you'll get an alcohol, a primary alcohol. But if it is a secondary or tertiary, you'll end up with an alkene instead. So it's an elimination reaction, as opposed to a substitution reaction to get an alcohol. Since the carbon that's attached to the halogen is only attached to one other carbon, it is a primary alkyl halide. And so we won't go down this route, we will instead go this way. Alright, so it's a primary substitution, creating a primary alcohol and some sort of salt. Alright, so this OH and this Br are going to switch places during the substitution reaction. As usual, I like to convert my condensed diagrams into a line diagram. Just make sure you have the right number of carbons. 1, 2, 3, and then the bromine. 1, 2, 3, and then the bromine. And then the 1-methyl group popping up from the top. Just double check you got the right number of carbons. Like I said, that's a very common silly mistake that students will make on a test. Now the bromine and the hydroxide will switch places, giving me a primary alcohol where the OH group is latched on here. And the bromine is now latched onto the sodium, making sodium bromide, which is our hydrogen halide, also known as the salt. So there you have it, primary alcohol, salt, just the same as on our chart. The primary alcohol is created and the salt is also produced. Alright, feel free to try the rest out yourself, and we will continue on with the other remaining chemical reactions in our next video.